So thank you everybody for coming today to hear the talks of our Friends Prize winners. Before I introduce them, let me just tell you a little bit about the Friends Prize. This is usually part of a visit by the Friends of Harvard Math, which is a group of people who donate to the math department. And kind of just as I've become chair, I've come to realize how exceptional and important this is. Math is something that most people in the world are kind of afraid of, and anything that shows us in a good light and brings us to the public, even our own public, is a wonderful thing. The Friends see great value in us, and they have funded things, especially this particular prize, to help us do that. So this prize is awarded every year to one or two senior theses, and the main criteria in the prize is sort of academic excellence, but also people that can communicate math very well. So we're lucky this year to have two exceptional speakers, Kenz Kallal and Lux Zhao. And the first talk this afternoon will be by Kenz on the Selberg trace formula and some applications to arithmetic statistics. So,
okay, I unmuted myself. Let me share my screen. So, first of all, thank you for the. Oh, did it work? Can everyone see my screen? Is it?
I think. Does he need to be given permission to share?
Oh, I tried it earlier. Let me try it again. Okay, now it should work. Yeah, so thanks everyone for the invitation, and Professor Hopkins for the introduction. So my thesis is about some questions in number theory, and I was advised by Professor Kissen. So I want to begin with an example of one of my favorite examples of a kind of very concrete question in number theory. So this is a Diophantine equation which asks for solutions in integers to a particular equation, say x squared equals y cubed minus 2. And I'm going to explain why such a concrete question is relevant to the arithmetic of a certain ring. So I'm going to explain the relevant fact about the arithmetic of a ring, which is that this ring that you get from adding the square root of -2 to z is a UFD. Its elements up to units factor uniquely into irreducible elements. And so let me explain why this fact is so useful in this concrete setting. It's because you can rearrange the equation and factor it over this ring. And then you can observe that these two elements of z adjoined the square root of -2 are co-prime. And then using the unique factorization property, you can conclude, for example, that each of these factors, but you only need one of them, is a perfect cube. And by expanding the right-hand side, you can conclude directly that the only solutions to this equation are plus or minus 5, 3. Okay, so in particular, using the arithmetic of this ring, we've deduced kind of a very non-trivial property about this equation. I mean, we've figured out all of its solutions, which I don't know of any other method to solve this problem. Okay, so in general, in algebraic number theory, we're interested in number fields. So the example we did above was the number field q adjoined square root of -2. And number fields have rings of integers. Has ring of integers, which is usually called OK. So the general invariance that we're interested in is called which is called a class group. There's a class group. Okay, and so this is usually denoted CL of K. And what this invariant does is it it controls the failure of OK to be the ring of integers to have the unique factorization property. Okay, so there's many other concrete examples in the one I gave above for why this invariant is so central to understanding the arithmetic of number fields. Okay, and so we can ask the question. I mean, what are these groups CL of K? So can we compute them? Can we compute the structure of these groups? And of course, there are algorithms to do this, but the real question is, what kind of theoretical understanding can we obtain about this? So the most famous result was conjectured by Gauss, but only proved quite recently by Heegner, and a gap in the proof was filled by Stark. So that kind of finished in 1969. And the statement is that the imaginary quadratic fields, there's actually only finitely many with trivial class group. So one example, which I didn't prove why I had trivial class group, but one example is this field Q adjoins the square root of -2, this one, which has trivial class group. So there's actually a finite list. It's Gauss knew that there were finitely many, but it was only shown later that they are exactly this list of number fields. Okay. So that maybe that gives you some hope that maybe we can understand these sorry, I should say trivial class group. Okay. Maybe that should give you some hope that these things can be understood very well theoretically, but this is kind of a fluke. So for example, if in the real quadratic case, it's not even known. So it's not known if there are finitely many. If there are finitely many, this seems like an important thing we should know if we want to understand the arithmetic of quadratic fields. Finitely many. Okay, with trivial, we're looking only at trivial class group here. And I should add here that sort of it's conjectured that there's actually infinitely many, and that in fact around 76% of real quadratic fields K have so okay. So there's that, and what this conjecture suggests, the fact that somehow we're able to make claims like this, suggests that maybe like a more reasonable question is to ask what do these class groups look like statistically? So what is?
Can I intervene with a quick question? What's the difference between square root of -2 and square root of -8?
Oh, okay. So this is like sort of an issue relating to the discriminant, right? So these numbers D are actually you make a very good point. These numbers D are supposed to be the discriminants of the imaginary quadratic fields with trivial class group.
I see.
So they're not exactly these numbers D, but
So two
sorry.
shouldn't be there?
Yeah, I think two shouldn't be there.
Okay.
Now, or like the problem is this is kind of a list that like is like always floating around. Like I'm actually a little bit confused now because why?
It should be 3, 4, 7, 8, etc.
Yeah, sorry. Sorry, you're right. I just copied the list incorrect. See, like this is very good. Yeah, that's my fault.
Okay, thank you.
Wow, that's very embarrassing, right? Like this is such a famous theorem, right? And somehow I just like completely. All right, thank you for that question. Okay. Oh, did I? Okay, yeah. So the real question is, what are their distribution? What do they look like statistically? Okay. So on average, and what does their distribution look like? So, and this is sort of one of the central questions of the field of number theory called arithmetic statistics. So that's what the title is. That makes sense, right? It's looking at the statistics of arithmetic objects. So if I want to state like another sort of famous thing, and I hope that I won't say something wrong. So this is the sort of the central conjecture of this area, which is called the Cohen-Lenstra heuristic. So this is from 1983, and it says that the probability that a imaginary quadratic field has the P part of its class group. So here P is an odd prime, isomorphic to some given abelian P group A. So A is an abelian P group. This is supposed to be proportional to the inverse of the size of the automorphism group of A. So there's a general sort of heuristic that these objects that occur kind of randomly should do so with probability inversely proportional to the size of the automorphism groups. And I mean, even this conjecture is kind of very, very far from being resolved. So maybe I can say that like the case, now I've gone from P to L. I should use P, okay. The case P equals 3 is sort of partially resolved by Davenport and Heilbronn. So they showed at least that there's a positive proportion. They showed that the probability that, and they gave a specific lower bound, but so where P is equal to 3, but this is greater than 0. But even in this special case where we ask like what percentage of these imaginary quadratic fields have a trivial P part of their class group, it's unknown. It's unknown if a positive proportion have trivial P part if for larger primes P. Okay, so this is sort of like one of the big questions of arithmetic statistics, is to kind of make this not unknown. Okay, and then the second thing I want to kind of talk about in the direction of questions is the issue of asymptotic averaging. And here I'm gonna state it in terms of real quadratic fields. So I started with imaginary. Now I'm doing real. So we would like to understand averages where we're ordering by discriminants of the sizes of class groups of imaginary quadratic fields, of real quadratic fields. So these are D. And like Gauss tried to do this, and he kind of noticed that no good asymptotic law existed as t goes to infinity. But he was able to make a conjecture, which is that if you weight this average by another invariant called the regulator, then you could end up with a good asymptotic law, which is actually this is asymptotic to t to the 3/2. So this was conjectured. This statement was conjectured by Gauss based on computational evidence, and then proven by Siegel in 1944. So I mean, there's kind of a second sort of important question is can you get rid of can you get rid of the dependence on the regulator of this thing? And that's like a question a lot of people have tried to study, which is still unresolved. So the theme of my thesis is about using the theory of automorphic forms to try to attack these questions. So I want to say like one or two things about what that means. So one sort of example that you might be familiar with is the example of Fourier analysis. And what that is talking about, or part of that theory, is the theory of the Hilbert space of square integrable real functions on R which are invariant under Z. Okay, and the point of like the theory of Fourier series, for example, is that this decomposes as a Hilbert space direct sum. This has a basis given by exponential functions. That's the point of Fourier analysis. But in general, I mean, you have a theory of automorphic forms that comes from the more general L2 spaces, right? About where you have a group, and then you look at the functions that are invariant under the action of a discrete subgroup. So the key example here is looking at this L2 space of functions on SL2R, which are invariant under SL2Z. Okay. And sort of the main object of study in the theory of automorphic forms is a representation of SL2R. So an action of SL2R on this Hilbert space, which is the right regular representation. So what that means is that the action of an element of SL2R on a function just sends it to that function, but where the inputs are acted on the right by the G. So this is sort of this regular representation is where all the automorphic forms live. And when you study the representation theory of this thing, in general, one thing that's very useful is given a test function, some smooth test function in here, you can consider the operator called rho of phi. Okay, and all this is an averaging of phi over the group G. So G is now my shorthand for SL2R, where you just average the action. Okay, maybe this is I really want to write them in the other order because this I want to put a function next to on the right of rho of G, right? Okay, so these operators are actually very nice. So they have a tendency to be compact and things like that. So they're they're very profitable when you study this representation. So finally, now I can state a version of the trace formula. So the general idea of the trace formula in all of its forms is it's a formula for the trace of this operator. Okay, but of course, I mean, this is a Hilbert space, right? What's the definition of the trace of an operator on an infinite dimensional vector space, right? There are many, many analytic issues that need to be worked out in order to make the trace formula make sense, right? Just to make both sides that converge, usually, unless this quotient is compact, you need to do some kind of truncation procedure, which I won't talk about. But anyway, this part is called the spectral side, and what you get on the right hand side is you get a sum over conjugacy classes of your discrete subgroup of these integrals of over G mod the centralizer. So I'm going to note the centralizer of a particular conjugacy class is just a subscript, and then you're going to integrate the conjugate of that thing by the element of G. Okay, so just some terminology. This side is called the geometric side. And these integrals are called orbital integrals. So, right. So the left-hand side is really, makes sense why it's called the spectral side, right? It's about eigenvalues. And the right-hand side usually, in concrete cases, tells you things about the geometry of G. All right. So just to give you an example, if you replace SL2Z with Z and an SL2R with R, what you recover from this formula is what you expect to get something from Fourier analysis, and that's what you get. You get the Poisson summation formula if you do this. So you get that the sum of your test function applied at the integers is the same as the sum of its Fourier transform. That's a very useful thing in number theory. So we kind of know we're on the right track, like once we've done this. Okay. So the last thing I want to do now, maybe the next 5 minutes, is to talk about how you can apply sort of the methods of the trace formula to attack the arithmetic questions that we talked about at the beginning. Right. So I want to start with real quadratic fields, and in that context, where maybe looking at the upper half plane in the complex plane, right? And this guy has an action of, oh, that's weird. Okay, well, this guy has an action SL2R, which is transitive, and you can show that the stabilizer of I is SO2R, right? So this is why SL2R kind of, the group that we're looking at, the representation theory of is sort of present in this theory. And so that means that if you take a quotient of H by some gamma, so for example, gamma is SL2Z, right? Some discrete subgroup of SL2R, then this is really a double coset space of SL2R, right? And if you apply the trace formula, so what does the trace formula say in this case? Well, there's a spectral side and there's a geometric side. So what you get in the spectral side is you basically get information about about differential equations. So in particular about the eigenvalues of the Laplace operator. So that's what shows up there. And on the geometric side, you get information about closed geodesics on your double coset space. Okay, I'll just in shorthand I'll write it like this. So somehow like now the names really make sense, right? The spectral side is about eigenvalues and the geometric side is about, well, the geometry of this manifold. So using this, and here, I mean, when you talk about a closed geodesic might loop over itself more than once. So you define a prime geodesic to just be a closed one that only traces out its image once. So what the prime geodesic theorem says, it's this beautiful analog of the prime number theorem in geometry, which lets you count the number of prime geodesics on these surfaces. So actually, this theorem doesn't just hold when gamma is SL2Z, it holds as long as this double coset space has finite volume. But I'll just write it like this in shorthand. So it lets you count them, the prime geodesics of bounded length. So maybe length less than log t, and it says that this quantity is as t goes to infinity is asymptotic to t over log t. So actually, the statement is like the same as the prime number theorem somehow. So what Sarnak did, so this is one of the results of Sarnak's thesis, was he used this to show a result about class numbers. So he attacked this asymptotic averaging problem for real quadratic fields by applying this, right? And he found basically the point is that the regulators of quadratic fields, or real quadratic fields, are basically the same as lengths of geodesics on this surface. So what you're able to show now is, well, maybe I can use something more reasonable. What he was able to show using that theory is that this is asymptotic to some constant times t squared over log t. Okay. So that's like, but of course, like I haven't told you, like how am I summing these things? I pay the cost. I've removed, or I didn't do it. Sarnak did it. Sarnak removed the dependence on the regulator in the weighting, but now the problem is that you have to order them by regulator instead of discriminants. Okay, so maybe that's its own thing, and you can also apply. So in imaginary quadratic fields, so this is the last thing. There's also a technique that you can do to produce, so one application of the trace formula, which is called the Eichlersulbert trace formula. What you get here is the trace of a Hecke operator on modular forms. So trace. And what you get here turns out to be a linear combination of class numbers, okay, of these quantities, sizes of class groups. So what you're able to do is you're able to exploit these identities that you get to deduce that there's infinitely many of these imaginary quadratic fields with p part of their class group trivial. So this technique that I've explained works in special cases. That's sort of part of the original content of my thesis, special cases. So it works when p equals 5, 7, or 11, which I think is already pretty good, considering that the only cases in which positive density results are less than that, right? Yeah, so that's the results. So that's kind of the overview. I hope that was informative for everyone. I'll stop sharing. Yeah, okay.
All right, thank you, Kenz. Oh, thank you. Maybe I'll just take a minute to see if there's any questions. I'm reminded the beginning of your talk, talking about class groups and unique factorizations. This is my segue into history, reminded me of a conversation I was having with Dick Gross about the origins of number theory. And he remarked that if the fields Kummer had studied, the cyclotomic fields, had unique factorization, he was trying to solve Fermat's last theorem. If he'd been successful and they had unique factorization, we wouldn't have much of modern number theory. And so this, I always love hearing the story you told at the beginning. Barry, you should correct me if I was wrong, since this is being recorded.
No, you're absolutely right. In fact, if it were not, let's put it this way, as low a number as 23, where his sort of partial proof of Fermat's last theorem got into trouble because of non-unique factorization, that would also be a problem.
And now that I hear you say that, maybe it was you, not Dick, that said that to me.
And as I recall, for 23, you can still make it work, but things really begin to go awry at numbers like 37, where the class group has a factor of the same p.
Oh, well, so that started all those many years ago, and we just heard about new original research in the same area. All right.
The results that Ken started with about a square and a cube differing by 2, that I think goes all the way back to at least Fermat claimed that.
Oh, wow.
Yeah, it's a challenge he gave to the English mathematicians.
Mm-hmm.
Oh,
So I guess he was French, right? And
yeah,
he wanted to prove that like, the English mathematicians didn't know what they were talking about.
Threw math problems in their general direction. So, okay. Anyway, thank you very much. And now we move on to Lux, if you're ready. Lux Zhao, who's going to tell us about the history of mathematics and the axiom of choice.
Thanks so much, Professor Hopkins, and also thanks, Kenz, for a great presentation. So I'm going to move in a rather slightly different direction. I'm going to bring everyone to the world of history of math. So a little bit about how I arrived at this topic, and what you're about to hear is, as both a history and math concentrator, I've always wondered how we can incorporate history into the understanding of math in a non-trivial way. And, a lot of times we hear, this mathematician, Fermat, Gauss, propose all these amazing theorems and amazing results, and we don't really know that much about what's going on in their lives and what the context was for when they proposed this. So I thought that the axiom of choice would be a great subject to lead us into sort of examining how we can incorporate time and history into our understanding of math. So, sorry. So I imagine a lot of you are very familiar with the axiom of choice already, but it's a very controversial axiom that was proposed by German mathematician Ernst Zermelo in 1904. So the axiom basically says that for any set X of non-empty sets, there exists a choice function f such that for every set A in X, f of A is an element of A. So basically, we can see that if X contains finite numbers of sets, it's pretty obvious because we can just enumerate all of the values for such a choice function, and it's immediate that this holds. But when X contains infinite many sets, the axiom of choice, AC, is not immediately evident. And this is also why the British philosopher and mathematician Bertrand Russell, he tried to sort of popularize this axiom for a general public. And he was writing a book while serving in prison. And he said to choose one sock from each of infinitely many pairs of socks requires the axiom of choice, but for shoes, the axiom is not needed. So basically, it's very subtle, right? It's also a very well-known way of presenting the axiom. So in the case of shoes, we can easily just say that this choice function is determined by choosing the left shoe of each pair. Whereas for socks, there isn't, usually there isn't really a distinction between left sock and right sock. And so it makes it very difficult. And in order to specify this choice function for infinite pairs of socks, you would have to literally make the choice for every pair. So that is initially what was troubling mathematicians. And it turns out that AC also has many interesting equivalents in set theory and outside, such as the well-ordering theorem, which says that every set can be well-ordered. And in graph theory, every connected graph has a spanning tree. So it has many interesting results and equivalents that are sort of a bit surprising for many that were looking at it. So why do we care about it, right? So one of the most, so on the left, you can see there are David Hilbert, Ernst Zermelo, Jacques Adamach. I'm trying to tell the names just by looking at the pictures. Henri Lebesgue, Bertrand Russell, Émile Borel, René Bert, and Henri Poincaré. There are 8 of the examples of many, many mathematicians that really debated about the legitimacy of the axiom of choice at the beginning of the 20th century. One of the reasons is that it was soon found out that it leads to a very puzzling paradox called the Bonakitarsky Paradox, which basically tells us that if you accept the axiom of choice, then there is a way that you can deconstruct a unit ball and reconstruct it into 2 unit balls of equal volume. This is very counterintuitive for many people. And so one of the first questions that really makes the axiom of choice relevant in many years to come is that should an axiom be accepted for its applications despite its counterintuitive results? Other axioms before the axiom of choice refer back to the very intuition of math, but the axiom of choice doesn't really seem to have a very solid foundation or a reason for us to believe why it has to be true. And also the second question that's very relevant is, what is existence? Does the choice function or something like it exist if we cannot explicitly construct it? So as we will see, this is actually a question that's central to the concerns of many, especially French mathematicians that had trouble accepting this axiom. So my thesis is a joint math and history thesis. So it has to, I sort of structured it in a sort of gradual way. The first chapter is about a group of French mathematicians, but mostly focusing on their personal context, interpreting why they really objected to this axiom. And the second chapter is about our favorite Kurt Gödel, and sort of how he was able to come up with the relative consistency proof of AC in a period of personal turbulence as he migrated from Austria to the US around World War II. And the third chapter is more about the modern developments after Gödel from the 60s to today, and how the different dichotomy theorems and ultimately the ultimate L conjecture today points us, and how it ties back to the very first debates on this axiom. So the first chapter really surrounds about these 3 mathematicians, Borel, Baire, and Lebesgue. We've heard of them in many different, we all know the Lebesgue measure comes from Henri Lebesgue. And in fact, they're all very prominent analysts in their times. It's very interesting because they all went to the École Normale Supérieure, and Borel was sort of personal mentor advisor to both Baer and Lebesgue. So they have very interesting interpersonal relationships. But unfortunately, Baer and Lebesgue didn't have as prominent as a career in their contemporary times as Borel. And we will see a little bit of the interpersonal drama that's in this time period. So one trend, one phenomenon that was pretty remarkable at the beginning of the 20th century is that French mathematicians were treated as elites, and they oftentimes served as public figures. So on the left, you can see this is a painting of members of the French Academy after a session crossing a bridge from Palais de l'Institut, which is also where the French Academy of Sciences meet. So, you can see that they're very distinctive from everyone else. And on the right, even more remarkably, Paul Painlevé, the mathematician some of you might heard of, he actually served as the wartime prime minister of France, which not everyone associate with the identity of mathematician back then. And so this is an era of phenomenal fame and public responsibility of mathematicians. And as a result, there is a sort of circle of elites around these really prominent Parisian mathematicians, and which is also where the young generation of mathematicians really aspire to join, because it promises all of the resources and maybe potentially opportunities to serve their country as well. So moving on to Borel and Baer and Lebesgue, they are historically known in the history of Axiom of Choice as the opponents of the axiom. But in my thesis, I actually looked at both their public letters and their private letters to each other, and I found my historian's hat on, I found some discrepancies that were very interesting. So in their published letters, they presented the very typical arguments we just saw, right? Borel said that, okay, the arbitrary choice might have to be made infinite times. And Baer said all analysis should be reduced to the finite. It's very, very sort of fitting into the stereotype of an analyst in the start of the 20th century, being a finitist and constructivist. But in fact, in their private letters, they seem to be actually, at least before 1905, which is when they published these 5 letters opposing the axiom of choice, they seem to be really proponents of set theory and the transfinite compared to a lot of their predecessors. So in my chapter, in the interest of time, so what I found was that they were facing very fierce interpersonal competitions, and especially the resources for someone who was from the provinces and not Paris was very limited for mathematicians who wanted to make it into professorship at a Parisian institution. So it was even though that they were, very interested in set theory, and they were sort of proponents of set theory and the new methods of the transfinite and infinite, they couldn't really, they had to sort of hide it a little bit. And I'm happy to talk more about the historical argument here and the observations if any of you are interested. But basically this chapter finds that they are sort of, instead of opponents, they are sort of frustrated proponents, and the attitude towards AC actually were influenced by a lot of social and personal pressures. So in the second chapter, I talk about Kurt Gödel, which many of you know as for his incompleteness theorems. We all know that he's a very famous logician, but his contribution in set theory was also very remarkable. And what he did was basically legitimized the axiom of choice mathematically by proving that it's consistent with other set theoretic axioms that we already had. So the proof sort of was very complete in 1940 when he published it, and it's a very interesting structure, very elaborate, 8 chapters of moving from the very basic axioms of set theory all the way to proving that proving that the axiom of choice and the continuum hypothesis are consistent with, are relatively consistent with the set theory axioms. And how he showed it was very interesting. So basically, he constructed an inner model L, where basically, it sort of models the universe of sets, which we call V here. And so the way he proved the relative consistency of AC was that he said if V is L, which is an axiom that describes, that L is actually the universe of sets. If V is L, this axiom and other basic axioms lead to a contradiction, then in this model L, the relativized version of this axiom, VL is L, and other relativized basic axioms would also lead to a contradiction, right? Because L is supposed to be this inner model that replicates whatever is in the universe of sets. And so if there is a contradiction in the bigger universe of sets, then in this inner model we constructed, all these axioms, the relativized versions of these axioms would also lead to a contradiction. But we know that the relativized version of V is L is within L, and L is derivable from all the basic axioms in our universe. So the contradiction must already lie in our basic axioms that we started with. So this is very interesting, in a way, very indirect way of proving the axiom of choice, because it's sort of, a lot of mathematicians wondered why Gödel made such an indirect path around the axiom of choice and created all this model around it. So to understand why he did this, we actually have to look at his life. So Gödel was born in a very wealthy family in Vienna, actually a little bit outside of Vienna. And he grew up as a very well-read kid. He had interest in, physics, politics, philosophy, and economics. He had a lot of interests, and he grew up, obviously he went to the University of Vienna, where all the prominent philosophers and scientists, mathematicians met. And he was part of the Vienna Circle with many other prominent scientists and philosophers. And it was there that he was immersed and contributed in this meta-theoretic atmosphere at Vienna, meaning that he was not only able to focus on his own theories, but he was able to transcend the boundaries of his own theories and everybody else's theories and arrive at a theoretical perspective that was very rare for the philosophers and scientists in the Vienna Circle. And so his stature was definitely first felt at the Vienna Circle. And then something very surprising and tragic happened in 1938. He was married, but to a Jewish girl in Vienna. And we all know that 1938 was also the year that Hitler took over Austria. So because of his marriage, he actually had to move to the US in order, to save his wife. So he moved to Princeton at the Institute of Advanced Studies, and he was great friends with Einstein, and he had a lot of great scholar friends that, that was really fans of his, and he had great conversations with people. But unfortunately, he, at being at the IAS, he didn't have any teaching responsibilities, and that sort of led to a period of really severe mental instability. And towards the end of his life, he was very paranoid mostly about the early period of his life, and to an extent that he would trust nobody but the economist Oscar Morgenstern, who's also from Vienna. And in this period of mental instability, he also started exploring into the field of philosophy. And that is also sort of the background of his endeavors in set theory. And he started to have all these theories of, of philosophers like Leibniz and Edmund Husserl, of them being prosecuted genius, and that their contemporaries were trying to sabotage their work, which is pretty remarkable. And he found all the evidences, performed his task like a historian, found all the archival materials to support his theories. So basically we can see that, you know, from his meta-theoretical background in Vienna to really a period of personal insecurity at Princeton, those are all sort of the things that he was living through when he proposed the proof. So let's take another look at the proof now. So you can see that he did two things here that are you can find parallels or traces in his life. So the first one is that he, like we said, he built an inner model that is supposed to parallel our parent universe. And there are more evidences in my thesis, and I'm happy to talk about them. But I found that this is an amazing parallel with his own search for personal security. And by building something like L, like the sort of very solid inner universe, he was able to really find value in math that supports his own search of security while at Princeton, while experiencing all the effects of migration and insecurity. And the second thing that's very remarkable is that he proved on the right, he proved that there's this notion of the absolute. So he proved that, you know, things like L and the V is L axiom not only holds in our universe, but also holds in the universe that we create. So this notion of absolute, you can see, also traces back to his contributions to the Vienna Circle, has a very similar taste of, you know, being meta-theoretical and looking for things that hold across different theories, across boundaries. So this is sort of what I did in my second chapter. Is also a snapshot into what Gödel was up to when he, what led to him proving the consistency proof in the way that he did. And finally, in the third chapter, I looked at some of the more modern developments of the axiom of choice. So the first development after Gödel was that Gödel was wrong. So it turns out that in the context of large cardinals, Gödel's V is L no longer holds. So in the interest of time, I'm not going to present all the definitions of the large cardinals. So basically, we found that if considering the existence of really large cardinals, this axiom of Gödel's, which is the premise of his proof of the axiom of choice, no longer holds, which means that his proof of the axiom of choice was also no longer relevant. So what happened was set theorist Dana Scott proposed this theorem. So assume there is a measurable cardinal, then V is not L. And further, there is what evolved to be the dichotomy theorem, which tells us basically that L is either very close to V, the universe of sets, or very far from the universe of sets. And in context with the Scott's theorem, it just really seems that Gödel's assumption of V is L is not very valid. But Gödel did propose a very promising path for constructing a model that leads to the axiom of choice. That would also solve the problems of the axiom of choice not having a solid foundation, intuitive foundation for the French mathematicians. So what's the next step after Gödel being proven wrong, and can we actually still find the right axiom following his path? So it turns out that Gödel had a prophetic notion that's called the ordinal definable, which is defined as the class of all sets which are definable from ordinal parameters in the hierarchy of the universe of sets. And so this is basically, in other words, he improved his notion of definability, and he arrived at this more general notion of, or like model of the ordinal definable OD that is more general and more likely to be closer to the universe of sets than L. But what we found later is that OD is in fact not an inner model. So in a way, in other words, it means that V as OD cannot genuinely be true because OD cannot genuinely be a candidate for the universe of sets. So this axiom might, still be relevant, but it would not provide the intuitive foundation for the axiom of choice like we hoped. So what do we do next? We find actually a sort of inner model within OD that's contained within OD that's called the hereditarily ordinal class HOD, which is the union of all transitive sets M such that M is in OD and M is a subset of OD. So basically we find we really like OD, and we try to really still use it, but carve out a portion of it that we could use. So HOD is now an inner model, but is V is equal to HOD? So that's the axiom we're trying to explore after V is L. And it turns out that in a similar spirit with the L dichotomy theorem, we could find a HOD dichotomy theorem by strengthening the closed notion of the L dichotomy theorem. And it seems that, again, we can prove that the HOD as a model is either very close to V or very far from V. And a lot of other evidences shows that, leads to this conjecture, HOD conjecture. It is provable that if there exists an extendable cardinal, then from the ZFC axioms, our basic set theoretic axioms, it's provable that the far option of the HOD dichotomy is vacuous. So again, but this is a conjecture that's more likely, more hopeful than the L situation. But again, we might need to find stronger evidence. So that leads to our final candidate, which is the ultimate L, which is proposed by my advisor, Professor Wooden. So V as ultimate L is defined using the property of Baire and Lebesgue measure. So in a way, it's a full circle bringing together, the intuitive analysis notions of Baire and Lebesgue. And this axiom, as stated here, we won't go very further into details, but basically what we found is that this axiom V as ultimate L would lead to, would again lead to the axiom of choice, would imply the axiom of choice. But with the additional perk that the ultimate L conjecture, as proposed here, is either true or false. So in a way that we have basically translated the entire question of the axiom of choice into whether the ultimate L conjecture is true or false. If it's true, then V as ultimate L is very promising because the ultimate L conjecture shows that it's provable that there exists an inner model N such that N models V as ultimate L. So in a way that it could be a very genuine axiom that is the right axiom after V as L. But if it's false, then we know that V as ultimate L does not hold because it basically says that you can't prove that there is an inner model N such that N models V as ultimate L. So basically, if we take N to be V, the universe of sets, then the third clause of this this conjecture tells us that V as ultimate L does not hold in V. You cannot prove V is ultimate L in V, which tells us that V is ultimate L does not hold. And interestingly, because of the way that this conjecture is stated, it is either true or false because there either is a proof or there isn't a proof. So here again, we're at crossroads and we don't really know exactly if we will provide intuitive foundation that would satisfy all the opponents or failed proponents of the axiom of choice in history. But at least such a historical approach tells us that, it's the axiom of choice didn't come from nowhere, and it's not just something that mathematicians today either assume or discard in their proofs. So I hope this is helpful, and there's a cartoon that for everyone it's not Halloween, but hope this is this helps with understanding the Axiom of Choice. Thank you very much.
Thank you, Lux. It's always good to have an XKCD cartoon. Thank you. Well, gosh, that was really a great talk. Axiom of Choice is one of those things you learn as a young person and find yourself scrutinizing it in a unique way. And I suppose partly it's because it's a question about mathematics that's trying to be a math question. And anyway, it was really a pleasure to journey with you through this constellation of ideas, intellects, mathematics, and lives that go into thinking about this question. So thank you. Thank you. I think that concludes our business. Maybe once again, I'll just thank Kenz and Lux. Maybe we can all thank them once more. And I will pass this back over to Dusty. Are you the master of ceremonies here?
I don't know if that's my role, but I mean, I guess I'll thank everyone for coming and thank Lux and Kenz again.
Can I ask a question before we disperse? So I've read or been told that there was a moment of tension when Gödel was about to taking his citizenship exam, because, so you know where I'm going with this.
Yes.
Do we know exactly what is the logical flaw that he supposedly found with the American Constitution? And does this, would you relate this to his other, you know, what's the word? Paranoid, possibly paranoid theories.
Yeah, I think I was able to, personally, I was able to find some, there was a slip of his sort of citizenship record that states that this in fact happened. And I think another department concentrator who just graduated, Lucy Wang, I think she wrote something about this exact topic. And yeah, I believe it's very fascinating. I don't know personally how it relates to the rest of his philosophy, but I would definitely think that it was already developing, and it kind of shows that he's genuinely interested. He's very excited about being a U.S. citizen, which was kind of, you know, a shared sentiment by a lot of like emigre scientists back then. But it also shows he's genuine interest in political science, and yeah.
But you
Thank you very much.
Well, thank you. I should have said at the beginning, although I did clap. But you don't know specifically what that path to what's called the path to dictatorship or other kind of logical flow
No,
was.
Unfortunately I don't. But I think Lucy's thesis would contain a lot of it.
I think there is some mention of it. Is it in Lucy's thesis? Yeah, probably.
I think so, yeah. But it's definitely, it's like between anecdote and serious argument for sure.
Okay, thank you.
Well, okay. All right. I guess if there's no more questions, Dusty, somebody has to.
All right. Well, thanks, everyone.
Wait a minute.